first of all, Ohm's law is very simple. It basically states that you have a voltage drop, which is a product of the current and the impedance flowing, or the impedance and the current flowing through it. Now, the impedance, originally Ohm's law stated that voltage is equal to the current multiplied by the resistance, but the resistance can be replaced easily with a complex impedance, and this basically it still causes a voltage drop across that element, that particular element, but this voltage drop doesn't lead to dissipation. So you can see over here, this the red plus and minus gives us a voltage drop across X and R, the combination, where X is an inductive reactance and R is simply a resistance, and each of them will have their own voltage drop, of course, with the difference being that X cannot dissipate energy. It's simply an energy storage element, and R does dissipate energy. And if you want to dissipate energy or transfer active power, there must be an exact phase between voltage and current. So this is always the case with the resistor. That's why it dissipates. With an inductor, they are always 90 degrees out of phase. It's similar with a capacitor. So then, when they are out of phase by 90 degrees, there's no dissipation. It's simply reactance. In other words, it stores energy and then releases it in the next half cycle. So this is just some basics on Ohm's law for complex impedance circuits. So here you see Ohm's law just in a different way. Current is voltage divided by impedance. And impedance can be written, generally speaking, by R plus JX, where X can be any reactance made up of any combination of elements, capacitors or inductors, or any combination of those. Now you see we do have this J operator. We remember that we looked at complex numbers last time. The complex numbers basically represent, or if we use it in the context of impedance, the complex part then represents the reactive part, and the real part, the imaginary is reactive, and the real part is resistance. So you can see over here, then we just have the definitions, and J is the complex number, square root of -1, and it represents this quadrature phase shift of 90 degrees. So we did discuss all of these concepts in our first webinar. Now it's just applied practically to a practical circuit, where it actually starts getting some meaning, and you can actually start seeing the power of this complex representation technique. So what we have here is a source voltage. It's a sinusoid, and then we've got a resistor and an inductor in series. Now, according to Ohm's law, each of these will have a voltage drop across it, and there will be a current, of course, flowing through R and L. Now, the current through R and L must be identical, because it's only one current loop. The current cannot disappear. So IR and IL is equal, as you can see over there. But the phase difference between the voltages and the currents are not the same. You'll see the phase difference between IR and VR, which is the voltage across the resistor, is exactly the same. So there's no phase difference. Phase angle is 0, and then the phase angle between the voltage across the inductor and the current is 90 degrees, as we said previously. So you've got only energy storage over there, but over there in the resistor you've got energy dissipation. Now we can represent this on a complex plane. Remember we said, okay, all the real numbers are on the x-axis and the imaginary numbers are on the y-axis. So resistance would be there on the x-axis, and inductive reactance will be here on the y-axis. Now if we combine these two in one single element, we find then Z, which is a complex impedance, and it's a complex number that you can represent on the complex plane like this. Now Z has a magnitude, which would be simply the length of the arrow, and it also has an angle relative to the horizontal axis. Now this is just another example. We have a capacitor instead of an inductor, and you can see that the voltage across the capacitor and the current is 90 degrees out of phase, but now it's the other way around. In this case, the voltage lags the current, and in the inductive case, the current lags the voltage. Okay, so capacitive reactance given by this equation. If you look at the problem over here, we want to calculate the capacitive reactance of a capacitor of 30 microfarad. So it's very simple. C is equal to 1 over 2 pi of C. You already have the capacitance, so it's a simple calculation. C, the reactances are always given in ohm. You can see why when we go back to the definition. Remember, R is always in ohm, and therefore X must also be in the same unit, and Z will also be in ohm, but Z will be a complex number. Alright, so in this example, maybe just quickly show where it comes from. Omega C is the original definition. So if we say 1 over omega C, this gives us the capacitive reactance. But of course then omega is an angular frequency, and then we can multiply normal frequency, which is time changing, 1 over period, as we discussed last time. Multiply that by 2 pi, which is a complete circular rotation, then this gives us angular frequency. So this is actually where this 2 pi fc comes from. So what we have, we say, okay, yeah, it's a 50 hertz signal, so the f would be 50, and then we just have 30 micro, which is times 10 to the minus 6, and then 2 pi, and we just divide, giving us 106.6. I just want to switch to the calculation application, which is Python. I did briefly show you this last time. Let me just see. Now the problem is I don't have all the numbers with me. I think, what was it, 30 microfarads. And then the blackboard slide disappears, so let me see. F is equal to 50, so I'm just going to define all of these numbers. So then we want to calculate XC. We say XC is equal to 1 over 2 pi F multiplied by C, and C has already been defined. So this should work. Pi is not defined. Let me just quickly run this program, webinar 2. Because the reason why it doesn't recognize pi is because it's in the numpy module, and it hasn't been imported yet, so it should actually recognize it now. Let's say C is equal to 30 microfarads, F is equal to 50, and XC should be calculated now as 106.1 ohm. So let me just go back. Yep, there you go. So you can see it's 106.1 ohm roughly. And then you can draw this, of course. XC would be a negative reactance. Oh yeah, I forgot to show you why this is so. Let's quickly go back to this slide. Actually, because it's a complex number, or an imaginary number, let's do it over here. Perhaps we've got a little bit more space. So let's say we've got a impedance, inductively speaking, so this would be then equal to 2 pi FL, or maybe let's just make it omega. It's quicker to write. So we've got omega L over there. But if you make it an impedance, in other words, this changes to a Z, then this means you have now the complex operator combined with this. Now, okay, the same thing happens with capacitance, but everything is divided by 1. So you've got this 1 over j omega c, like that. The thing is, if you multiply, we don't like j's under in the denominators. We don't like that. So what we do is we multiply by j over j, which is the same number. Of course, you just cancel it out. Now, if you do this, you see j multiplied by j gives you -1, and therefore this is equal to minus j, which is then the j in the numerator over there, divided by omega c. So this is then the expression for zc, and remember that xc is equal to 1 over omega c, so therefore zc will be equal to minus j xc, like that. And where xc is, of course, defined on the previous slide, like that. Okay, so this is why the capacitive reactance is negative. You'll see then the inductive reactances are always positive on the complex plane, right? So let's go on. You see over here we've got complex impedance. You see it has inductive impedance because it's a positive imaginary number. Alright, here we got a capacitive reactance again. We see, for our example, we have a 50 ohm resistor and we have 100 ohm capacitive reactance. And then we just simply do the calculation, the magnitude and the angle of this complex number. So let's just perhaps run through this. Xc is now 100. Just remember these numbers quickly. Or perhaps, you know what I should do? Is actually open the PowerPoint in the background. Perhaps the problem is if I switch, I can't see the exact number. So let's go. Got it now in the background. So here we go. I'm going to switch again to Python. And I should be able to look at the numbering as well. So what we see here is that we've got an R of 50 ohm, right? And we've got an XC of 100. Okay, and then of course the impedance is very easy to calculate. It's simply the square root of this is Pythagoras, so it's r squared. Now in Python you write square by a double star plus xc double star 2, which will give you, actually I should have written this as let's say mag or z magnitude. Alright, so that should work out to, well, around 112 ohm as it says on the slide. You can also then calculate the angle simply if you look at the triangle there as the cosine of r over x, or sorry, r over z. So if you quickly do this, it should work. R over the z magnitude, which we have just calculated, and that gives you 0.9. Actually, let me just write this differently. I'm going to do an angle, well, maybe let's call it EF for power factor, because this is exactly what it is. It's R over Z. Okay, let's see what that is. That's 40.44, which is not very good. But what we can do now is say, right, the power factor is equal to cos phi, so phi would be equal to the the inverse or arc cos of this. So see if this works out. All the pi factor. So pi would be that multiplied by 180 divided by pi to convert into degrees. Then you get next 63.4 degrees, which is what we have also in the slide. So let's jump back. You see then how the calculation is basically being performed over there. So this is then what the answers we get. It's 112 ohm, and the angle over there is minus 63 degrees. Or just 63 degrees if you just indicate the direction, doesn't really matter. Now, of course, you can combine these things any way you want to. Over here we've got an R and an L and C, they're all in series, and of course all these currents are the same. Voltages will be different according to the impedance. And so you can see that the R is always on the real axis, and both XL and C would be on the imaginary axis, but one would be positive, one would be negative, and so just basically subtract one from the other. Then we've got series impedances, like resistance. Z is also just added for series. So this is a very simple calculation for 3 different resistors, 10, 24.5, and 33.2. To get the total resistance, we just simply add them. We get 67.7 over there. Now, this is a little bit more complex. We've got total impedance calculation, where we have to calculate the 27 ohm resistor, 120 microfarad capacitor, and a 5 millihenry inductor. So I'm going to switch again, but before I do this, I think I'm going to do the numbering quickly offline. So we say L equals 5 millihenry. I'll show you this now. C is equal to 100 microfarad, 120 microfarads, right? So that's that, and R is equal to 20 something 7, right? So now we say now these are all in series, so it shouldn't be too difficult to calculate. So I'm going to switch to Python so we can do the calculation together. Okay, so you can see here in line 20, 21, 22, I have defined L, C, and R. You see we use the E operator to indicate times 10. So 5 millihenry we indicate by 5 times 10 to the minus 3 in Henry, right? And C would be 120 microfarad, indicating that way. Now, what we have for a complex impedance would be then simply R as it is, plus J times the inductive reactance, which would be 2 pi, if it's been defined. Otherwise, we will just do it afterwards. 2 pi f multiplied by L. Capacitive reactance is minus J multiplied by 1 over 2 pi fc. So, but we can, well, we don't have to have a 1 there. We can just say J divided by 2 pi f and c, like that. So this should work out. Right now it complains about J, so I'm just going to place a 1 there just to indicate that it's a complex number, so this should work out to 27 and on the real axis and 24.9 negative J axis. Let's see, I'm going to remove this, it's just confusing. Let's switch back to Blackboard, and there you get 27 and minus 24.9 J. In other words, the real component or the resistive component of the impedance is only resistive over there, so you can see it doesn't affect. But the reactive component is a combination of the inductor and the capacitor, and you can see that it's an influence. They do influence one another. Okay, so that's that calculation. So for impedances in parallel, you got this equation 1 over the total resistance is simply the inverse of all the resistances added together. With impedance, it's the same. Remember, impedance is actually just a complex resistance, if you want to call it that. So example, 350 and 250 ohm resistor network is added together or combined in parallel, so we calculate the total resistance like this. Very easy. The same with impedance, but it's a little bit more complex. Because I only have half an hour, I'm not going to go through this one with you, but it's the same calculation that we had before. In essence, well, actually, because it's already there, maybe we can quickly do this. It's the same values, so let's do this. We have 27 ohm resistor, 50 millihenry capacitor, inductor, and 120 microfarad capacitor. So let's switch. It will be actually quite nice to see. Right. So we've got, just to recap, we've got L 5 millihenry, C is equal to 120 microfarad, and R is equal to 27 ohm. Now what we want to do is get a Z for a parallel combination. So what I'm going to just say Z inverse would be equal to 1 over R. I'm actually going to copy now from that calculation there. So that would simply be an addition, which would be 1 divided by that impedance that we had before, minus just trying, I hope I don't make a mistake over here. Just the inverse of this. That should be okay. Let's just have a look. Another reason. I think that doesn't work. Yeah, sorry about that. Python does not like to divide by integers, so you have to explicitly say 0.0 to indicate that it's a real number. But anyway, it seems to work now. So if you want now, remember this is actually 1 over Z. So now if you want Z, you have to simply invert the inverse impedance, and it should be that number. I hope it works out right, otherwise it's simply a numerical error, and we probably have to then move along. Okay, that's the parallel combination. It doesn't look the same though. Now I'll put this in, so I have a script file, I'll put it in the script file as well, which will be available on Moodle. I don't want to spend too much time looking for the error now. But you can see the general idea. We already have these calculated, and we just take the inverse. And then after this, we take the inverse of the sum again, and then get the total reactance, or the total impedance.